Before discussing the practical application of elevated temperature, I'd like to touch briefly on why elevated temperature should be the method of choice for reducing HPLC runtime. The theoretical benefits of temperature were predicted in an Antia and Horvath's seminal paper published in 1988. Shown here, the graph plots the effect of temperature on runtime while keeping all other factors, including retention factor, the same. The graph predicts a 20-fold improvement in runtime can be achieved without loss of resolution when the temperature is elevated from 25 to 200 degrees Celsius. How does temperature speed up a separation? Elevated temperature reduces mobile phase viscosity and improves mass transfer. This graph shows the effect of temperature on the viscosity of some common reverse phase mobile phase components. The exponential change in viscosity from 20 to 200 degrees Celsius results in very low back pressures at elevated temperatures. Lower back pressures at higher temperatures allow for faster flow rates. Faster flow and higher mass transfer rates translate into significantly shorter runtimes without loss of sample resolution. This theory is applicable to both isocratic and gradient separations. Elevated temperatures also increase the elution strength of water. This allows the user to use less organic, lowering the cost of the analysis and improving the environmental impact of the analysis. Recent studies have shown that running hot eluent into a mass spec detector without cooling can improve method sensitivity. A poster detailing one such study by LCMS Limited can be accessed at any time on the ZirChrom website. Several separation conditions must be met in order for the theoretical advantages of high temperature to become a reality. First, the stationary phase must be stable at elevated temperature. ZirChrom reverse phase columns are very thermally stable. Both the ZirChrom PBD and the ZirChrom polystyrene phases are stable up to 150 degrees Celsius. The ZirChrom carbon-coated phases, Diamond Bond C18 and ZirChrom Carb, are stable up to 200 degrees Celsius. To demonstrate the stability of ZirChrom phases, our ZirChrom PBD phase was exposed under constant flow and mobile phase helium sparge to a temperature of 150 degrees Celsius. Periodic injections of a set of standards were made to measure column performance. This test was discontinued at 7,000 column volumes after no significant column degradation. Stability is also required for the compounds you wish to analyze. Many users will eliminate the possibility of using high temperature for this reason. However, the compounds don't need to be completely thermally stable. The separation only requires that the compound be stable for the period of time that the sample dwells in the column. A compound that is not thermally stable at 100 degrees Celsius for longer periods of time may demonstrate acceptable stability at 100 degrees for the column dwell time of runs expedited by high temperature. Finally, the instrument you choose for the analysis must be optimized for elevated temperature. Extra column volume should be minimized whenever possible, and we recommend using a heater that has been optimized to eliminate thermal mismatch band broadening. Thermal mismatch band broadening occurs when the temperature of the mobile phase on the perimeter of the column is a different temperature than the center of the column, causing a thermal gradient across the column. This radial temperature gradient causes peak broadening and virtually eliminates any possible benefits you may have gained by using an elevated temperature. Thermal mismatch band broadening most often occurs due to the lack or inefficiency of the column heater's mobile phase preheating assembly. In this slide, we show an extreme example of thermal mismatch. A set of alkylphenones are analyzed and a ZirChrom PBD column at 165 degrees Celsius. The first chromatogram in blue shows an instrument with an optimized column heater that includes a mobile phase preheater. The second chromatogram in red uses a heater without a mobile phase preheater. Although the broadening effect is most noticeable on the later eluting compounds, all peaks in the chromatogram generated without a preheater fall well short of the separation achieved with the instrument that included an optimized preheater. Let's look at Horvath's theory in practice. In this case study, we present the analysis of a set of 6 antihistamines on our ZirChrom PVD column using an instrument with an optimized column heater. In the study, when the temperature is increased, the flow rate will be adjusted to keep the pressure drop constant. The initial chromatogram, using a method temperature of 21 degrees Celsius, gives good baseline resolution of all compounds in 12.5 minutes, with a pressure drop of 195 bar. The resolution of the critical pair, designated 2 and 3, is 2.1. Our first increase in temperature is modest, only up to 50 degrees Celsius. This modest increase in temperature requires the flow rate to increase to 2.2 milliliters per minute in order to keep the pressure drop constant. When we inject our analytes, we see Horvath's theory in practice. Resolution between the critical pair is maintained at 2.1, and the full analysis is now just 5 minutes. This experiment is repeated at 80 degrees Celsius with even more dramatic results. Resolution between the critical pair is again maintained, and now, with a flow rate of 3 mils per minute, the full analysis is complete in 2.5 minutes. The final separation was run at 140 degrees Celsius. The critical pair resolution is still 2.1, the pressure drop is constant, and with a flow rate of 4.2 mils per minute, the analysis time is now less than a minute. Here is experimental proof of Horvath's theory. Elevated temperature with constant pressure allows shorter runtime while maintaining resolution. Speeding your analysis through column heating not only preserves resolution, it also preserves your bottom line. Using the ZirChrom quantitative value assessment tool, we analyze the cost savings of speeding your separation using temperature. The tool takes into account labor, materials, and instrument time cost savings. As you can see, at 80 degrees Celsius, a modest increase in temperature, there are significant savings per analysis. For the best results, we recommend the following safety precautions when employing elevated temperatures. It is important to ensure flow through the column throughout the whole separation, both heating and cooling. Under heat and without constant flow, the mobile phase in the column may evaporate, causing column degradation. The back pressure of the system must be sufficient to prevent the eluent from becoming gaseous. We recommend using elevated temperature for analytes that are stable at the desired temperature and dwell time of the separation. A good starting point for learning more about analyte temperature stability is the 2002 analytical chemistry paper by Thompson and Carr. Finally, at temperatures above 100 degrees Celsius, we recommend employing a helium sparge. At very high temperatures, oxygen can form damaging free radicals that may shorten the lifetime of your column. This slide is one of our show-off slides. This chromatogram is only possible on a zirconia-based phase. First, a high pH phosphate buffer was used to render these basic analytes net neutral, defining the primary mode of separation as reverse phase. Then, a temperature of 150 degrees Celsius was used to speed the separation, allowing for baseline resolution on our diamond bond C18 column in under 30 seconds. Elevated temperature is a powerful tool for increasing your lab's productivity and bottom line without sacrificing resolution. As heating technology is readily available on most existing instrumentation, the cycle time benefits of elevated temperature can be achieved without acquiring expensive specialized equipment. The unparalleled stability of ZirChrom phases allows for the use of elevated temperature without the worry of compromising the particle. Want to learn more about the unique selectivity of ZirChrom phases? A brief technology overview discussing the surface chemistry of ZirChrom phases can be accessed at any time on the ChromeU page of the ZirChrom website. Thank you for completing this ChromeU webinar. On the ZirChrom website, you can access our full ChromeU webinar series, use our free Buffer Wizard tool, or learn more about ZirChrom products and applications.